Hey everyone, and welcome back to The Explainer. I am super excited to be your guide today on behalf of Forge College. So go ahead and grab your hard hats and maybe your favorite drafting pen, because today we are diving deep into the literal engineering blueprints of smart contracts. Now, if you remember our previous lesson, we got into handling state changes and rollback semantics, right? Basically how blockchains go in and undo mistakes when things inevitably go wrong. Well, today we're taking that a step further. We're looking at the exact architectural rules that actually trigger those rollbacks in the first place.
Because really, it's kind of the ultimate mystery of execution constraints, isn't it? When our transaction is just humming along perfectly and then suddenly rolls back, completely undoing all of its local changes. Who exactly pulled the plug? Was it the CPU? Did you just run out of memory? Or did you accidentally touch a piece of data you really weren't supposed to? Well, today we are going to demystify exactly what specific resource limits trip that alarm during an execution failure. And crucially, we'll see how the underlying architecture, whether that's the Ethereum virtual machine or the Sealevel virtual machine, decides to enforce those limits.
Okay, here's our blueprint for today's explainer. First, why blockchains need limits. Second, budgets, buckets, and gates. Third, constraints in the EVM. Fourth, constraints in the SVM. Fifth, optimizing your smart contracts. And finally, wrapping up and next steps. Let's get right into it. Section 1. Why blockchains need limits. So at their core, blockchains are highly shared environments, right? We're all using the same space. And at the most concrete level, runtime constraints essentially boil down to three core categories, just to keep the network healthy. First off, we absolutely have to prevent CPU monopolization. We simply cannot have a single transaction hogging a validator's CPU time indefinitely. It just wouldn't work. Second, we have to stop unbounded stack and memory growth. Think about it. If a transaction could infinitely expand its memory, it would literally crash the node. No way around it. And third, we absolutely must control persistent state reads and writes. Reading and writing to the blockchain's hard drive, its state, is incredibly taxing. So ultimately, these limits are absolutely crucial because they are the exact mechanisms that keep transaction fees from just spiraling into infinity due to bad actors or accidental infinite loops.
All right, moving on to Section 2, budgets, buckets, and gates.
I want you to think of your compute and instruction limits as a budget. It is quite literally a wallet full of fungible currency, like gas on Ethereum or instruction quotas on Solana. As your code executes mathematically heavy operations or runs down hot paths, you are spending cash straight out of this wallet, literally handing it over. And if that wallet goes empty before the code finishes, well, execution halts, the transaction fails, and the state rolls back. You really have to treat your compute budget with the exact same care you treat the real cash in your pocket. Next up, we have buckets. Buckets basically represent your capacity containers for grouped resources. So you have a stack bucket that holds your call frames, a memory bucket for your transient temporary data, and an account data bucket for the persistent bytes that live on the blockchain forever. And the golden rule here, and I cannot stress this enough, is don't spill your buckets. Seriously. If you design a contract that repeatedly shifts megabytes of data back and forth, or if you use some deep recursion that just keeps stacking call frames, your buckets overflow, and boom, once again, your transaction crashes. Finally, we have gates. Think of scheduler gates as overly strict bouncers standing outside a very exclusive club. Before your transaction is allowed to make any progress whatsoever, these bouncers check your ID. They verify that all your prerequisites are met. Did you explicitly declare which accounts you are going to access? Do you actually have enough in your gas budget to even enter the building? If you haven't declared your permissions properly, the bouncer doesn't argue. They just point you straight to the exit. Which brings us to Section 3, Constraints in the BVM. Let's start with a magic and, honestly, slightly terrifying number, 1024. This is the classical EVM's fixed stack depth limit. It is a rigid, non-negotiable architectural code that you absolutely do not want to violate. If your smart contract enters a recursive loop and tries to stack, say, 1025 call frames into its stack bucket, well, the bucket spills. The EVM throws an exception right then and there, and your execution is instantly reverted. Game over. Now, what's really crucial to understand about the EVM is exactly how it manages state. It relies on sequential execution. It processes transactions one by one, single-threaded, and resolves any conflicts simply by the order in which they arrived. Because of this, it uses a global state trie. Any contract can theoretically access global storage via opcodes. But, and here's the kicker, because everyone is basically waiting in a single file line to read and write to this giant global database, storage rights are treated like premium real estate. They are notoriously expensive. You must carefully manage your gas budget, because if you write to storage too often, your wallet will drain incredibly fast. Let's flip the page. Section 4, Constraints in the SVM. So where the EVM is strictly sequential, the SVM aims for fine-grained parallelism. It's a totally different ballgame. Let's look at compute first. The EVM uses a global transaction gas limit, whereas the SVM applies per invocation budgets for its parallel threads. Now, when it comes to memory, the EVM charges you as your linear memory expands. But the SVM, it gives each program its own isolated memory regions. And crucially, looking at state, instead of the EVM's global slot reads and writes, the SVM requires explicit account declarations. You have to tell the network exactly which accounts you plan to touch before you do absolutely anything. So the pivotal point here is the timing of our gates. You know those bouncers we talked about earlier? In the EVM, the gates are implicit, and they happen during runtime execution. You usually find out you're out of gas while you are already running the code, which means, yeah, you pay for the compute you wasted before failing. Ouch. But in the SVM, enforcement relies on early pre-flight checks. The scheduler acts as a gate before the compute even begins. If you misdeclare an account in the SVM, the bouncer rejects your transaction before you even step foot inside, which actually saves you from wasting those precious compute resources. All right, let's put this into practice. Section 5, Optimizing your smart contracts. Let's imagine a real-world scenario where you need to update the balances for thousands of users all at once. Because the underlying architecture dictates your optimization levers, your whole approach completely changes based on the system. On the EVM, if you try to batch all of that into one giant transaction, you are for sure going to blow through your gas budget and spill your memory bucket. So EVM optimization essentially forces you to do off-chain aggregation just to reduce those on-chain writes. On the SVM, however, you are actually rewarded for splitting the work up. As long as you are updating disjoint, separate accounts, you can just distribute those updates into multiple parallel transactions, completely maximizing the network's throughput. It's a real game changer. And this creates two very distinct, very critical workflows for developers. Step 1, for EVM developers, you have to be highly defensive at runtime. You absolutely must guard your expensive loops and double-check state keys mid-execution just to protect your gas budget. Step 2, for SVM developers, your most important work happens before the transaction is even sent. You must rigorously verify your account lists and access permissions to ensure you can actually pass the scheduler's pre-flight gates. Section 6, Wrapping up and Next Steps. If you take one thing away from this explainer, I want you to remember this underlying truth. Enforcement timing changes failure modes. It's absolutely brilliant when you think about it. The architecture of the blockchain entirely dictates whether a failure wastes your compute budget during a runtime revert or prevents the compute from happening at all through a pre-flight rejection. Sequential runtimes like Ethereum expose a lot more runtime exceptions, while parallel schedulers like Solana shift a huge chunk of those failures to pre-execution rejects. So here is your ultimate highly focused checklist to keep handy. If you are building on the EVM, your primary goal is to cut storage writes and heavily minimize opcode-heavy loops. If you are building on the SVM, your goal is to minimize account churn, carefully size your accounts for rent economics, and precisely declare your access. And honestly, no matter which environment you're building in, always map your logic back to your budgets, your buckets, and your gates. Which leaves us with a pretty provocative thought to ponder. How will these exact runtime limits shape your transaction cost models? Now that you know exactly how gas, memory, and state access are constrained, how does that translate to the actual dollars and cents of deploying code? Well, that is exactly what we will tackle in our next module on cost drivers. Until then, thank you so much for joining me on this explainer. To dive deeper into this subject and explore a wealth of other Web3-related topics, please visit our website at forge.college. I'm your host, signing off on behalf of Forge College, and I will see you in the next lesson.